Welcome to Knowledge with Sarfaraz KWS.
When the right inorganic salts meet concentrated acid, the solid matrix breaks down to release these deep red, fuming vapors. In qualitative inorganic analysis, we use this reaction for one specific purpose: identifying ionic chlorides in an unknown salt mixture. This is the Chromyl Chloride test. But the brilliance of this protocol is that we don't actually track the chlorine itself. Instead, we use the chloride ions as a temporary vehicle to move a chromium atom through a precise chain of custody, shifting it through a series of distinct, color-coded physical states. To trace that chain of custody, we have to start at the lab bench. Understanding how this test works requires looking past the red smoke. What we are really building in that test tube is a calibrated chemical filter, designed to separate one specific halogen from all the rest. The protocol requires exactly 3 starting materials: the unknown salt, solid potassium dichromate, and concentrated sulfuric acid. For the reaction to initiate, the unknown salt must be an ionic chloride, like sodium chloride or potassium chloride. An ionic lattice will freely dissociate to provide the chloride ions required for the reaction. If the target is a covalent chloride, like carbon tetrachloride, the structure holds its chlorine atoms too tightly, and the reaction never starts. Highly insoluble chlorides, like silver chloride, fail for the same reason. The glassware used for this mixture must be entirely dry. Even trace amounts of moisture will cause the intermediate compounds to hydrolyze before they can ever leave the tube. By combining these reagents in a moisture-free environment, we create a highly acidic, strongly oxidizing matrix designed specifically to extract free chloride ions. When heat is applied to the bottom of the tube, the solid mixture transforms, volatilizing into the thick reddish-brown gas rising here. This equation details the transformation. Sodium chloride reacts with potassium dichromate and sulfuric acid to produce our red gas, Chromyl Chloride. Notice the chromium atom. In the dichromate reactant, it holds a +6 oxidation state. In the Chromyl Chloride product, it remains +6. Because no electrons are exchanged by the chromium, this first phase isn't a redox reaction. It is a complexation. This rotating model shows the CrO2Cl2 molecule. Chromium sits at the center of a tetrahedral geometry, double bonded to 2 oxygens and single bonded to 2 chlorines. This is a highly volatile, corrosive, and toxic complex. In this first phase, we have successfully bonded our target chloride to a chromium atom, creating a volatile complex that physically lifts the evidence directly out of the solid mixture. This raises an obvious question. Chlorine, bromine, and iodine are all halogens. Why doesn't this protocol produce a red chromyl bromide or chromyl iodide gas? The answer lies in the ease of oxidation. As you move down the halogen group, the ions become larger and hold their outer electrons more loosely. While chloride is stable enough to form the chromyl complex, bromide and iodine ions have their electrons stripped away by the highly oxidizing chromium sulfuric acid environment. Instead of bonding to the chromium, they are oxidized directly into diatomic bromine and iodine gases. The specificity of the test relies on this failure. Because the heavier halogens cannot survive the oxidizer without being reduced to elemental gas, the formation of the chromyl complex is uniquely specific to chloride. Merely seeing red vapor in a test tube isn't definitive proof. Other nitrogen-based contaminants, like nitrosyl chloride, can produce similarly colored fumes. To confirm the result, we pipe the red gas into a clear solution of sodium hydroxide. As the gas bubbles through, the liquid turns yellow. The color shifts because the Chromyl Chloride gas undergoes hydrolysis upon hitting the sodium hydroxide base. This produces aqueous sodium chromate, which gives the solution its vivid yellow color. For the final confirmation, we acidify this yellow solution with dilute acetic acid and introduce a solution of lead acetate. In this final reaction, the aqueous sodium chromate reacts with the lead acetate to drop out a heavy, bright yellow precipitate of lead chromate. By forcing the chromium through 3 distinct physical states and chemical environments, we create a sequence of nested conformations that isolates the result from any interfering vapors. There is a paradox at the center of this experiment. We perform this entire procedure to prove the presence of chloride, yet the final yellow solid used as the definitive proof, lead chromate, contains no chlorine at all. We achieved this by tracking chromium through 4 states, starting as an orange powder, volatilizing into a red gas, hydrolyzing into a yellow solution, and finally precipitating as a yellow solid. Throughout this sequence, the chloride ion acted as a transport ligand. It was a temporary, volatile vehicle used to smuggle the chromium out of the original test tube before being washed away. Because that transport vehicle, the chromyl chloride gas, is a liquid carcinogen and a severe respiratory irritant, this protocol must be performed in a properly ventilated fume hood. Ultimately, qualitative analysis is rarely about observing the target ion directly. It is about manipulating the chemical conditions to force an invisible ion to leave a macroscopic, undeniable footprint.